Welcome back everyone, and for this video I want to go over what many people consider to be the foundational paper for computer architecture, which is First Draft of a Report on the EDVAC by John von Neumann. Many people have heard about John von Neumann before. He's had numerous impacts across numerous fields. In the computer engineering world, one of the big reasons why we know John von Neumann is because of this idea of a von Neumann architecture. And this really stems from this paper right here. And so the first kind of question is, what is or was EDVAC? And so EDVAC is actually an acronym. It stands for Electronic Discrete Variable Automatic Computer. And what it actually was, it was the first stored program computer. And so there's the difference between a stored program computer versus a fixed program computer, say, is that as you could probably reason out, a stored program computer, you can change whatever the program inside the computer is to an arbitrary program to execute anything you particularly wanted, as long as it's supported within that instruction set, versus a fixed program computer, which it only does one thing. So you can think of a fixed program computer to be something like a calculator. A calculator is fixed; it does those only the operations that you give it. You can't. I'm talking about a simple calculator, by the way. You're very basic, like a 4-function calculator. It only does those 4 functions and takes only those inputs. It doesn't change. And so this was a really big deal. And one of the really big things to kind of note about this paper is that this paper is actually from June of 1945. So that's a long time ago now. That's getting close to about 80 years ago now. I guess a little closer to 75, but yeah, this paper is almost 75 years old now. But what we'll see kind of going through this paper is that a lot of the fundamental concepts and a lot of the fundamental ideas in this paper, they really persist. Even to modern architectures that we see today. Your modern Intel or ARM type architectures. And if another thing to note is this was a project, the EDVAC, that is, between the United States Army Ordnance Department and the University of Pennsylvania. So a common misconception is that John von Neumann is the founder of modern computer architecture, which is actually somewhat of a misnomer. He was a consultant on this project, and so that leads to him getting a lot of the credit for it. But in fact, this was actually the work of these two people, researchers at the time, Eckert and Mauchly. They started this in 1944, and this is reflected in the architecture community as the highest award you can win, the more or less Nobel Prize equivalent for computer architecture, is something known as the Eckert and Mauchly Award, not the John von Neumann Award. So they get that little consolation, and they also the great work that they did at the time. So I want to kind of go through this paper. We're going to skip over a couple chunks of this paper. The things that deal with vacuum tubes and magnetic tapes are not so interesting anymore. But the overall organization of this stored program computer is fairly interesting. So if we get to this, first we're going to go through this definition section. So the considerations which follow deal with the structure of a very high-speed automatic digital computing system. I'm referring to EDVAC. Especially its with its logical control. And so they make some definitions here that are fairly interesting. So they say that, an automatic computing system carries out instructions to perform calculations of considerable order of complexity. So, basically kind of the purpose of this project is they want to solve these difficult problems quickly, which, that's really the reason why, a lot of technology exists, is because we want to solve problems and we want to do it better and better. The instructions which govern the operation must be given to the device in absolute exhaustive detail, basically saying how the computer must be programmed. They include all numerical information which is required to solve the problem under consideration, initial and boundary values of the dependent variables, values of fixed parameters, constants, tables of fixed functions, basically just saying that, if you want to solve a problem, you have to give the computer all of the information. This is a punch card machine punched into the system of punch cards or teletype tape, magnetically impressed on steel tape or wire, photographically impressed on motion picture film, basically saying that, there are many ways that theoretically that you could feed information to this general purpose computer. Let's see. So moving on, once the instructions are given to the device, it must be able to carry them out completely without the need of further intelligent human intervention. So this is basically just saying that, we want to build a machine, or this is a machine that we don't want to have someone stepping in and constantly, pulling a lever, pressing a button, moving things around. We want it to work on its own. So it's worth noting, however, that the device will in general produce essentially more numerical material than the final results mentioned. Thus only a fraction of its numerical output will have to be recorded as indicated. Basically just saying that we don't care about all the intermediate values, we just care about the final values. So I think from there we can kind of move forward into, the more interesting parts of the paper. So we're going to start at section 2, which is the main subdivisions of the system. So let's kind of go through what they have to say here. So in analyzing the functioning of the contemplated device, certain classificatory distinctions suggest themselves immediately. First, since the device is primarily a computer, you'll have to perform elementary operations of arithmetic. So this section is basically just saying that because this is a computer, because we wanted to compute things, because this was actually partially commissioned by the U.S. Army to be used for calculating tables for, I believe it was for ballistics tables or something like that. They needed to be able to do math. So this just basically says that, it needs to perform these basic operations. So, your basic 4 functions, plus, minus, multiply, divide, as well as some operations that are fairly typical, things like square roots and cubed roots, things like logarithms and base 2 logarithms, natural logs, the sine function, as well as inverses. And so this is a very interesting part down here where they say, I'll actually highlight it, is that the first specific part, CA, referring to the central arithmetical part. And so, when they say central arithmetical part, it sounds very flowery, and a lot of this text is very flowery and can be hard to get through. But what they're really saying here is we want an ALU, an arithmetic logic unit, as we know in modern architectures. So that's basically all this central arithmetical part denoted as CA is. They also move on to say, we need some way of controlling this device of being able to, tell everything what to do is. And, that's another part they'll be very familiar, the second part being the central control. And so we start to see a lot of parallels with the with modern architectures. We start to see things that still exist today. We still have dedicated parts of processors that do arithmetic functions. We still have dedicated parts of processors that control things, that control how the pipeline progresses. So moving on. Third, any device which is to carry out long and complicated sequences of operations must have considerable memory. So another thing that is very apparent in modern architectures. Fairly simple, but it needs stating. This is the first paper on the subject in any event, so they have to say it. So, and not just say that they need memory, they need considerable memory. And this is something we even say today. Everyone's memory hungry. That's usually a bottleneck. And we can talk about that in another video of how that bottleneck has originated. So basically what we have so far is we have arithmetic, we have control, and we have memory. And so at least the four following phases. So these are just the phases that they say will need memory. So we can kind of skip over this. Okay. So to sum up the third remark, the device requires a considerable memory. Well, it appeared that various parts of this memory have to perform functions which differ somewhat in their nature and considerably in their purpose. It is nevertheless tempting to treat the entire memory as one organ and to have its parts even as interchangeable as possible for the various functions enumerated. This point will be considered in detail. One thing to note that if you decide to look up these papers as far as the references, because this is a first draft, not all the references exist. This is actually pieced together as best as they could, trying to figure out what John von Neumann was mentioning. You can actually find a scanned copy of the original hard copy of this online as well, which is fairly interesting to look at, but harder to get through because there's some pen markings on there, and you've got to deal with some handwriting, as well as the original typist, but still fairly interesting. So let's move on. So the three specific parts, your arithmetic part, your control part, these being considered together as a single unit, and then M as memory, correspond to the associative neurons and the human nervous system. And so this is a fairly interesting way of looking at this. So the most recent times when we think of neurons, what we typically think of, or what it's typically used for, is machine learning. But in a lot of ways, the common analogy to, a processor is, like a brain. And so, this is one of those early kind of biological influences, and, how this first computer was made, this thought of, they even say things like organs for, specific things to do a specific function. And then they also, like I said, they use, sense more like human organs, and then like up here where it says all about sensory and inputs, and different types of neurons. So a little hard to get through sometimes by reading it, but a lot of this is really just saying that, in many ways this is like the human body, and that, it makes sense to design it this way because this is what we know. So let's see what it says. So fourth, continuing on with his points, the device must have organs to transfer information from R into specific parts C and M. So let's see. Okay, so they define R right here. Let's see. The device must be endowed with the ability to maintain the input and output contact with some specific medium of this type. This medium will be called the outside recording medium of the device, R. So R is something just like what we call I/O today, just input output. So let's continue on. Like I said, fourth, the device must have organs to transfer information from R into specific parts C and M. That is the combination of arithmetic and control and memory. So, these will be things like buses in modern computers, the lanes that we transfer information from. So, moving on, the device must have organs to transfer from its specific parts C and M into R. So this is the output part of I/O. So, very similar things to what we have in modern computers so far. If you were to go in this blind, besides all the kind of wacky terminology, you would think that, oh, he's describing, modern processors. Okay, so the output information, which goes into R, represents, of course, the final results. These must be distinguished from the intermediate results. That's kind of what I mentioned earlier. At this point, an important question arises is, apart from its attribute of more or less direct accessibility to human action and perception, R has also the properties of memory. Indeed, it is the natural medium for long-time storage of all the information obtained by the automatic device on various problems. Why is it then necessary to provide for another type of memory within the device M? Could not all, or at least some of the functions of M, preferably those which involve great bulks of information, be taken over by R? So this is basically saying that if we're going to have, why do we need these two types of information things to store all our inputs to the system, as well as a separate thing to store all our outputs? How do we divide up the work? So let's just go back a little bit. So inspection of the typical functions of M show this. It would be convenient to shift the short duration memory required while an arithmetical operation is being carried out outside the device from M to R. Actually, A will be inside the device, but in CA rather than in M. So this is looking suspiciously like caches. So caches, are separate from memory. They're stored very close to your control and your arithmetic units, and it's the stuff that we're working on right now. So we're getting kind of an early look into thoughts about caches. So we can go ahead and highlight this right here. Actually, A will be inside the device, but in CA rather than MCF. Okay, all existing devices, even existing desk computing machines, are the equivalent of M at this point. Okay. However, logical instructions might be sensed from the outside. So let's see where they define I. I think I probably just means instructions, but it's always good to make sure, especially with these. Okay. Input. Input is I. Okay, that makes sense. That makes more sense than what I was thinking. Okay. So the latter may be conveyed from O to R when the device produces them output to that. I believe it was R reading the readable part. Am I correct in that? Let's see. Right here. Yes, the outside recording medium, R. Good. Okay. And in many cases, the possibility of using M accelerates matters decisively. But suitable blending of the use of M with longer range use of R may be feasible without serious loss in speed and increases the amount of material that can be handled considerably. More memory, you can do more. Very simple concepts, but very powerful concepts. the important thing to realize about a lot of these older papers is that while they can seem simple, the implications that they have can be very great. Okay, so indeed, all existing computing devices use R as a stack of punch cards or lengthy teletype tape, except for referenced above. Nevertheless, it will appear that a really high-speed device will be very limited in its usefulness unless it can rely on M rather than on R. So it must have the memory so it doesn't rely on somebody feeding it the data over and over. So it has to be stored within the machine for use and reuse. And then enumerations of certain limitations. Okay. So then we can kind of move on into this next section, procedure of discussion. So now that they've talked about, their basic ideas of input-output and or the ideas of input-output, having a control unit, having an arithmetic unit. What else did they have? Control, arithmetic, I/O, of course. I think I'm off when I said that this is kind of akin to caches. One could take it that way when they said that they're storing it. Actually, I think I'm correct in that sense. When they're saying about storing things more towards the control portion, the control and arithmetic portion of the processor. They don't mean caches in this sense, but it's the same idea of having data closer to where the actual computing is going on to reduce latency. So in any sense, we can think of that as a cache. Okay, so basically they're saying here that we've talked about, we've defined all of these things, so what's next? So they have to determine such discussion must bring out the features required for each one of these parts in itself, as well as in the relations to each other. So what they're saying here is that, now that we have all these pieces on a table, how do we connect them together? How do they work together? So 3.2, the ideal procedure would be to take up the 5 specific parts in some definite order, to treat each one of them exhaustively, and go on to the next one only after the predecessor is completed, which seems like a bad design, and which is immediately what he says. However, this seems hardly feasible, and it's pretty easy to see why. And it's pretty easy to see why modern computers don't do that. And it's because if we had this incredibly naive machine and we said that, each part of the machine is only 10%. So if we say that the ALU is only 10% of the processor and that the I/O takes up 10% of the processor and only one thing's running at the time, it's pretty easy to think that we'd get some pretty bad performance. If we're crunching on something in the background, we don't want to be literally stuck on I/O, and say if we have 10 other things ready to move on and be crunched by the ALU and spit out into memory, why do we want to be waiting on I/O during that time? So this is basically just saying that, of course, if we do this very easy solution, it has tremendously big performance overheads. Okay, so kind of moving on from that. In the course of such a discussion, the desired features and the arrangements which seem best suited to secure them will crystallize gradually until the device and its control assume a fairly definite shape. Nothing fairly interesting there. Okay, talk a little bit about checking errors. That's fairly interesting in a fault-tolerant computing point of view, but we can kind of move on. So here, elements, synchronism, neuron analogy. So here we have a fairly long, and I won't go over this entire thing in the video, but it's a fairly interesting analogy to the neuron and basically how inputs are treated by the machine, and how we can and how they kind of modeled them. And so it's a pretty exhaustive look at it, but we'll leave that to another time. So of course, if you're going to have the first binary machine or the first binary stored program computer, you have to define a lot of things, especially covering arithmetic operations. So here, let's see what they're going over. So let us now consider certain functions of the first specific part, the central arithmetical part, the CA. So this is, in this section, they're really just going to be going over, the design of an arithmetic unit. How they use binary, the sizing of, the sizing of what the kind of numbers they're going to be working with, be they floating point or integers, the number of steps to do these operations, and these are something that, because of how old these things, because how old a lot of these concepts are, a very introductory logic design class, you could understand a lot of how they built these adders and these multipliers, or maybe even a slightly more advanced, you could, really start to understand, the motivation behind the choices that they made. But we're not going to get too bogged in these details right now. Like I said, this paper has a lot of interesting information, but it is very outdated. So when they start talking about vacuum tubes or magnetic tapes, this is something that, while it's interesting to note what they did at the time, it's really the overarching ideas that we care about more. Yeah, what they're showing here is that multiplication, it takes a while compared to things like addition, I think is what they're trying to say here. The vacuum tube element, so we can kind of skip over these a lot of this section. So let's see what we have here at 6.0 E elements. Okay, the considerations of 5 have defined the main principles for the treatment of the central arithmetical unit. We continue now on the basis with some more specific and technical detail. So here they're just going over, how they're going to actually synchronize this thing, it being a digital machine that uses a clock. A synchronous machine, I should also say, uses a clock. Some little more into their neuron analogy, as well as going into the actual circuits for the arithmetical operations. So this can be fairly interesting to anyone that cares about this kind of work. I remember taking a graduate course on computer arithmetic that went from the basic types of adders to modern adders that we use today, and very, very fast types of adders, for reducing the critical path, or the critical path being the longest delay possible from input to output for a specific input. So we see over here, what I'm guessing is this is going to be a basic adder with 2 inputs, and then a carry-in input, and then an output. I believe in this paper they also go over, more or less the definitions of, proving, or the definitions proving, their arithmetic system and the designs that they use. So here they talk about things like delay units, that's specific to the implementation. We can kind of gloss over that. Multipliers as well. Discriminator. Let's see. and then more on the circuits for arithmetical operations. And so, this is more of that proof side of things, of kind of understanding how numbers are represented, how arithmetic numbers are represented in computers as binary digits, as unsigned and as signed binary digits, which we'll likely get into in another course, but I don't want to make this video too terribly long, even though it is passing the half-hour mark. Okay, some more on the divider circuits. And what we'll probably notice that's an interesting thing to note here, although we won't go into it in great detail, is that if you've noticed all the diagrams we've seen previously, we'll notice that the divider is a lot bigger. And the interesting note there is that division is actually, when we think of the 4 basic operations, division is actually far and away the absolute slowest, and that it's a very tough problem to crack as far as speeding division up. Addition is incredibly fast. Subtraction in binary and also in decimal. Subtraction is just adding a negative number, so very fast. Multiplication is another thing. Multiplication, you can build very fast multipliers that are based on addition. Things called CAMs. CAM actually has 2 different acronyms in architecture. CAM, in the sense I'm talking about, is carry array multipliers, which are fairly large, and power intensive, but extraordinarily fast. But then on a side note, CAMs can also stand for content addressable memory. So moving on, the binary point, a little bit more into binary and how those numbers are represented in the system. The circuit for arithmetic operations, other operations. Okay, so we get to see things like how they do square roots. So all fairly interesting information. I will encourage you to look at this when you have the time, but it's not really necessary to fine tooth comb look at everything, but just try to get the main ideas out of it. Okay, I'm still going over dividers. As this was a device used for arithmetic operations, it does take up a substantial part of this report. Okay, so this is where we finally move past arithmetic, it looks like. So capacity of the memory M, general principles. So we consider the third specific part, memory M. Okay, so they're talking about delay blocks, and so a lot of this, the capacity unit of memory is the ability to retain the value of one binary digit, one whole binary digit. Isn't that grand? We can now express the cost of various types of information in these memory units. Okay, so this is mainly implementation still. So basically breaking down, what do they need to store and how much it's going to take to store it. And then also picking things like, okay, what is our precision going to be on floating point in order to, do the same kind of cost trade-off, this cost-benefit trade-off. We can, theoretically you could have an infinite number of decimal points and you can be infinitely precise with a lot of these calculations, but there's always a trade-off. You've got to store that someplace, and that someplace is memory, and so you have to store how much you can store versus how precise, which is fairly interesting when you think about machine learning, because machine learning now, one of the very big trends is to use reduced precision as a way of packing more information into memory, instead of using things like floating point 32. A lot of times they're using things as low as int 8s. This is very interesting. Okay. So a little bit of the number of cycles it will take. Let's see if we can skip this. Okay. Get to the next important part. Sure do love to. Okay, here we go. Organization of M. Let's see what we have here. So we return to the discussion of a delay memory based on the analysis and conclusions of 12.6, which we skipped, and 12.7. The next task is then to discuss the terminal organs, A and SG. A is a 4-stage amplifier about which Moore said in 12.5. The function of A is solely to restore the pulse emerging from DL. Okay, so here we're just making sure that when we send information that, nothing happens while it's traveling, that, that information doesn't get, caught in the weeds or misinterpreted, or something happens and the information we get on the other side is fuzzy. The purpose of SG is this. At those moments, when other parts of the device are to send information to which this SG is attached, or when they're to receive information from it, SG must establish the necessary connections. Okay, so the SG, so we missed where they defined SG someplace, but it seems like SG is basically what's doing, what's controlling, all the buses in the system. I suppose it's not really important what SG is as far as, what SG does. Okay. So let's see if there's anything interesting to talk about here. Before we consider the E network of SG, one more point to be discussed. We allowed for only one state when SG is on, whereas there's actually two. First, when SG forwards information from M to C, from memory to the control unit. Second, when SG forwards information from the control unit to memory. Okay, in the first case, the output should be routed into L sub O and also into A. While no LI connection is wanted in the section, LI should be connected to A. Okay, so this is basically just saying about, how the different connections should be made, and should things be sent to the output, should things be sent to memory, and how that interconnection network should work. Okay. Fairly straightforward stuff. Okay. Some more interesting stuff. Memory and the control unit. Okay. Our aim is to go deep into the analysis of CC. Such analysis, however, is dependent on the precise knowledge of the system orders used when controlling a device. Since the function of CC is to receive these orders, to interpret them, and then either to carry them out or to stimulate properly those organs which to carry them out, it is therefore our immediate task to provide a list of the orders which can control the device, i.e. to describe the code and code words. Here we go. Another very foundational thing, code words. I wonder what those could be. So words that tell things what to do, or specifically have information to actually do something. So this is going to be your instruction set. So there's many different types of instruction sets out there. There's the ARM instruction set for ARM processors. There's the x86 instruction set for Intel processors. Microcontrollers generally have their own instruction set. PIC microcontrollers have the I forgot what it's called. I think it's just the PIC instruction set. Although I'm probably wrong on that. And then there's some other fairly frequently used ones for teaching. RISC and MIPS are typically taught in many universities. But yeah, here we have the first definition of an instruction set. So very interesting. Even as early as back then, these same topics exist. Okay, let's see. Okay, the orders which CC receives fall naturally into four classes. Orders for CC to instruct CA to carry out one of 10 specific operations. So I think that's just the arithmetic. Orders for CC to cause a transfer of standard number from one place to another. So that's just going to be loads and stores. Orders for CC to transfer its own connection with M to a different point in M. So this is going to be looking at different parts of memory and the purpose of getting its next order from there, and orders for controlling the operation of the input and output of the device. So controlling I/O. So these are all just instructions that we've all seen before. I/O type instructions, or dedicated I/O type instructions. Not like a lot of times memory mapped I/O that we have nowadays. But yeah, arithmetic operations, every ISA has things like adds, subtracts, shifts. I think it was defined someplace that there's only 6 operations you need in order to create a Turing complete machine. So, well, they certainly seem to have that. Okay. So here they're just going to describe, what these instructions end up doing and some more precise definitions. But the real key thing, so we don't spend all day, reading this 1940 era's flowery language, is that, basically they're making their own instruction set, which I believe they list at the end of the paper. Here we go, the code. Okay, here's something fairly interesting to note. So they break up minor cycles fall into 2 classes, standard numbers and orders. So just kind of like we have opcodes in instructions today, they say that we're going to have a way to differentiate between what is an instruction, what is a value we're loading, and not to treat a value or something incorrectly. We don't want to treat a value like an instruction. Okay, moving forward. Okay, let's see. These considerations discourage pooling several orders of a type alpha. Besides, this would not be logically possible either without intervening orders of the types beta. Okay, combining 2 orders of types is also dubious. So one of the things that you'll see a lot throughout this paper is they say that some things doesn't seem really reasonable or possible. And so what we'll see looking at later papers is that when they say of, doing things sequentially as the only way things make sense, which I think is a claim that they make in this paper, we'll see that modern processors actually, they gave that up a long time ago, back in I believe even as early as the 60s or 70s, when Tomasulo's algorithm came around and made processing out-of-order instructions feasible. So basically, out-of-order instructions means that it doesn't matter which way the instructions come in, they're going to be executed in a way that they can get it out the fastest. All right, so this is just going to be formulating the code. All right, so this is just kind of going over the instruction types. Okay. All right, I think that's really the end of the paper. Yeah, so, as we kind of saw from this paper, a lot of the ideas, that John von Neumann talked about, that Eckert and Mockley, as well as the many other people that, worked on the EDVAC project at the time, including John von Neumann, who was a consultant, some of these great innovations still exist today. And, that's the thing that I really want to impress, is that, all of these innovations that we see today, caches, victim caches, that was the idea of JOPI, and things like out-of-order execution, and, even the things going down as far as the processor design itself. Something that we even call, von Neumann architecture. This is something that was come up with in the mid-1940s, 1944 to 1946, it's this really thing that really puts it in perspective how far we've come, and and how these first principles are really really built in to computers today. All right, so that's going to do it for this paper. This is really a longer paper, as we can see, 42 pages. Most of the papers that I'm going to be going on that is more recent bleeding edge stuff, most of these conferences put a hard limit on 10 to 12 pages, so it shouldn't be a 45-minute video. But if you stuck around, thanks for exploring this paper with me. I'll make sure to link it below so you can give it a look. And if there's any questions or comments or concerns or anything, feel free to leave me a comment, and I will try to respond to you. Or if it's worthy, we can even do another video, really doing a deep dive into some of these topics. All right, thanks again for watching, and have a wonderful morning, afternoon, or evening.